So there's going to be three choices. There's always three choices for what happens to something when it dissolves in water. Either it has no pH effect, so it's pH neutral. It gives up a hydrogen, and so it's an acid because acids don't need a hydrogen, or it takes a hydrogen from water, and that would make it be a base. Okay. If the ion is actually hydroxide, that's a base, because a base is something that forms hydroxide in water. It doesn't have to form it from water, but hydroxides, when any ion that's a hydroxide ion is dissolved, there's hydroxide there. And so it automatically is going to make the hydroxide concentration go up because it came from the ionic compound. So any metal hydroxide, which was one of the types of bases that we went over last semester. And so if you just choose any metal hydroxide, and you figure out either it forms a solution, how much dissolved, or if it's a solubility thing, how much hydroxide forms, then those automatically are going to affect the hydroxide, hydronium concentrations, which will make the pH go up because it's going to be a base. Okay, so I have a little chart. This is Nairhood created here. If you don't like it, then create your own. But right here in the middle is like we have an ionic compound and there's a cation and anion. And what I have is I have 6 hexagons, and these 3 are cations and these 3 are anions. And so every compound you're going to find 1 hexagon for your base or your anion and 1 hexagon for your cation. So let's say it was sodium hydroxide. So you would have a cation and anion, sodium and hydroxide. So you would look here, sodium is a group 1A metal. And so this is the acid-base behavior of sodium. It is a neutral cation. It has no effect at all on the pH, just that positive. But your negative is hydroxide. That's a base. So it is going to affect the pH. If it was aluminum chloride, it is not a group 1A or 2A, and we need to see it or one of the metals not listed here. And so then we got to look over here. There is the aluminum ion right there. And so this is the behavior of aluminum. Aluminum is actually a weak acid. The aluminum ion is a weak acid, which means that it gives up a hydrogen. How does something that has no hydrogen give up a hydrogen? Is it just aluminum by itself? When the ion dissolves, they form ion-dipole intermolecular forces. It is not aluminum. It is aluminum surrounded by water. Remember when I wanted y'all to draw ion-dipole? There's aluminum. What part of water is attracted to aluminum? The oxygen. And so we are going to draw it so that the oxygen is close and I can't draw it 3-dimensionally because it's a piece of paper, but there would be above and below also. So I'm going to draw 4 of them this way, and then we're going to imagine that there's one above and one below. Okay, so there's also an oxygen right here and 2 hydrogens going up, and then below there's an oxygen and 2 hydrogens going down. So aluminum is in the middle of a bunch of water molecules. And what would be at the surface of the little ball that is aluminum surrounded by water? What would be on the outside all the way above and below? They are a bunch of, what are those? Those are H's. An acid is something that donates hydrogen, but this is not aluminum. This is aluminum aqueous. And so really it's aluminum that has really strong intermolecular forces with the oxygen. And that actually weakens the bond between oxygen and hydrogen enough that another water molecule that's not part of this little hydrated ion, another water molecule, when it comes in and interacts with one of these hydrogens, here, like that, this bond is so weak that a very tiny amount, very tiny amount of these situations will give up that hydrogen and make it go to there, which would create hydronium. It's acidic. If we took aluminum chloride and we dissolve it in water and we tested the pH, it is going to have a pH lower than 7 because it is acidic. It is not the aluminum that's acidic, it is the hydrate. And so all of these right here, every single cation that is listed here does the exact same thing. It forms really strong intermolecular forces to the oxygen in water, and lots of water molecules surround it because they have higher charges. Is this +3? These two are +2. But it's the intermolecular force, the ion-dipole force is so strong that it weakens the bond between the hydrogen and oxygen. And so when the hydrogens that are at the surface of this hydrated ion, when they interact with another water molecule, occasionally, for a very tiny amount of them, a hydrogen will go from this hydrated metal to the water. Okay. Chloride is one of these. It is a pH neutral anion. So if you dissolve aluminum chloride, the chloride doesn't affect the pH, but the aluminum does. So overall, it'll be an acid. So if one of them doesn't affect it, but the other one does, it's not like it's neutral and a strong base. It is a base. But you'll just look at the negative ion, you'll just look at the positive ion to see what happens. The other one is not going to change anything. Okay. So some cations and anions can exchange hydrogen with water to create either an increase in hydronium or hydroxide. So that makes it either acidic or basic. Some of them do not exchange, so there is no effect. If the ion exchanges hydrogen, then we then have to write it as an acid or a base separately. And so the way that we write things that are acidic or basic is a separate thing. Okay, so let's just look at this so that you can do a homework question. If it's a strong base, you don't have to do anything. If it's weak, though, you would. Okay, so if we have a solution of sodium carbonate, what are our ions for sodium carbonate? And this is a solution, so it's the one way. These don't exist as sodium carbonate. They exist as sodium and carbonate. Okay, and so it would be 2 sodium and carbonate. Okay. Determine which behavior each ion has in solution. So sodium, which one of these conclusions should we draw for sodium? It's a neutral pH, so it has no effect. If either one of them have an effect, though, the whole entire solution is that. So you don't separate the sodium from the carbonate in the water, they're just separated. Okay, carbonate. This is a process of elimination. Is carbonate hydroxide? No. Is it chloride, bromide, iodide, nitrate, chlorate, perchlorate, sulfate, or thiocyanate? No. If it is not any of these, then it is over here. Unless it has a hydrogen, then it would be over here. Okay, so an anion, every other anion there is, other than the ones that have hydrogen, would be a weak base. Almost every anion is a weak base. Only these 8 are not. And then occasionally, if there's hydrogen, they might be acidic. And so this is a weak base. So this forms ion dipole between the oxygens of carbonate and water, but then that ion dipole, a hydrogen can be exchanged from water to carbonate because it's a weak base. Weak bases accept hydrogen. And so this is from last week. If this is a weak base, if it exchanges hydrogens with water because it's acidic or basic, then you would show that behavior with water. So if we take carbonate, if our conclusion, this is a completely separate, this is ionization as it turns into ions. If the ion is a weak base, then you pick up that ion and you write it separately as a weak base. WB for weak base. Okay. A weak base will accept a hydrogen. And so if carbonate accepts a hydrogen, what does its formula become? HCO3 -1. Just what happens to the carbonate. Okay. Where does it get the hydrogen from? That water molecule. We'll just draw one water molecule because one water molecule is what exchanges a hydrogen. So if we take a hydrogen off of water, it creates hydroxide. So again, the weak base dissociation from last week or week before, you would write your weak base formula and you would add an H positive to it and rewrite the formula over there. The hydrogen is coming from water because it's the intermolecular forces. Occasionally, one of the hydrogens will come over. And so then you would take a hydrogen off of water and form hydroxide because the 2 parts of the definition for weak base that we need is a weak base accepts a hydrogen and forms hydroxide in water. This is going to affect the hydroxide concentration in the water because it's going to create hydroxides beyond water just creating them itself. Now you've got a thing that we dissolved in it. It's going to cause more water molecules to turn into hydroxide. Okay. So for homework, and we've already done this one, I want you to just write them as a positive, negative. This is not solubility. This is not solubility. This is, they're all aqueous. They've already dissolved. So acid-base behavior is after they've dissolved. You'll write the 2 ions and then underneath it, put if they're no effect on the pH or if they're acidic basic. And if it's hydroxide, you don't have to show it interacting to create hydroxide because it's hydroxide. But if it's one of the others, then you would write down, you would rewrite just that ion plus water. And so here are the choices. These are the cations that are neutral. If they're a metal cation that is not one of these listed, then the metal cation is neutral. If it is a polyatomic cation, it is a weak acid. So if it's a polyatomic ion that's a cation, and those exist, almost every medication that you take is a polyatomic cation. For things like allergies and other things, right? So like Benadryl. it is a polyatomic cation. Okay, it's a weak acid. Okay. And then if it's an anion, if it's a weak base, then you would rewrite it as a weak base. So we have these. What we're going to do on Wednesday is we are going to go over these. So I just want you to see if you can rewrite these. This is from the notes from the previous part, like what happens to it in water. Because for everything that we decide is an acid, either strong or weak, or a weak base, we're going to have to do the formula plus water. Okay, and then we're going to go over something called conjugate acid-base pairs. It's just a way to label things that are related to each other just by a hydrogen being different. And then we're going to do some calculations. And then eventually we will get to figuring out hydroxide and hydronium. And so we're going to do these practice problems on Wednesday. Whenever we don't fit, I got an example of almost each kind. But I've created the charts already. So I already have whether it's weak or not. If it's not weak, I have end. If it is weak, I have equilibrium. That says end, so I've already created the charts. Oh, this one, we needed extra column. I forgot to add the extra column to that one. Okay. So go back and finish the solubility stuff, and then